Hi, I would like to present our small contribution on simultaneous inference for autocovariances based on the autoregressive Sieve bootstrap. And this is joint work with Marco Meyer and Jens-Peter Kreis. We are from TU Braunschweig. So in a nutshell, consider a univariate time series Xt, strictly stationary, and we would like to do inference for the following statistic. So the max difference between, say, the autocorrelations of our process and its sample counterparts. And we would like to do this inference by applying a version of the autoregressive Sieve bootstrap. Possible applications would be to construct simultaneous confidence bands for the autocorrelations. But this paper is not limited to autocorrelations. You could replace those in equation R1 with the autocovariances, or even consider a version with lag window estimates of the spectral density to construct simultaneous confidence intervals for the spectral density. Another application would be to use the max deviation in order to do hypothesis testing, for example, to test for white noise. Two things I would like to highlight in the beginning. The first is we obtain results for the underlying process Xt, not necessarily being a linear time series. And the second thing is that the maximum lag in the max statistic, dn, has to grow with the number of observations in order that our result is valid. The bootstrap algorithm, the AR-Sieve, very quickly, given some data x1 to xn, after selecting an order p, depending on the number of observations, you fit an autoregressive model to obtain Yule-Walker estimates, and you use these estimates in order to construct pseudo observations x1 star to xn star, and with those you compute a bootstrap version of your statistic of interest. Repeat steps 2 and 3 sufficiently often in order to approximate the distribution of your statistic. And the question is, under which circumstances does this fairly simple bootstrap procedure work, and how does it perform in finite sample? So the idea that the AR-Sieve bootstrap may work in this situation is based on the following result. If you properly scale the max deviation, then you obtain convergence to the standard Gumbel distribution, and the scaling factors solely depend on second order properties of the underlying process Xt. And this result has been obtained from the result we use is obtained by Xiao Wu and published in 2014. And the nice thing about this result is that it holds for a fairly general class of processes. So it includes linear and nonlinear time series. And the second thing is that the rate of dn, so the max lag in the max statistic, is of polynomial order. And so from a practical point of view, the max lag can grow, for example, potentially with the rate square root of n, although it is directly related to the dependent structure of our underlying process Xt, represented by our physical dependence parameters alpha and alpha prime, as well as to Q, which is the maximum moment that exists, and we need at least a fourth moment to exist. In order to successfully apply the AR Sieve in this situation, we need the existence of the AR infinity representation of our underlying process Xt. A sufficient condition for this existence is given in equation 3. So this summability condition includes a parameter small r, which needs to be bigger than 1/2. And this parameter small r is directly related to the smoothness of the spectral density of the underlying process Xt. So an AR infinity representation of our process Xt is nice, although the dependent structure of the white noise ET can be quite complicated. The AR Sieve bootstrap, however, does not have to reproduce the whole dependent structure. We show that the bootstrap works if the bootstrap time series Xt star approximates well enough a companion process, an artificial process Xt tilde, which is a simple linear process. And so the dependent structure of Xt tilde is much simpler than the structure of Xt, although the autocovariance structure of both processes Xt and Xt tilde is identical. In a theorem, we give conditions for the bootstrap to work. So a scaled, so the AR Sieve bootstrap works for a scaled, properly scaled version of our statistic in the Kolmogorov distance sense if these two conditions hold, and these conditions basically relate the rate of dn, so the rate of the max leg of our max statistic, to two basic properties of our process Xt, namely the smoothness of the spectral density function R and a convergence property of the white noise of the AR infinity representation given by small beta here. In addition, this condition here gives sufficient lower and upper bounds for the rate of the autoregressive order Pn. So depending on small r and on beta, the rate for dn can be, for example, n to the power of 1/3 or even square root of n. Similar results are available for the autocovariances as well as lag window spectral density estimators. A quick remark, as I said, for our results to hold, it's crucial that dn grows with the number of observations. Suppose that this is not the case, so that dn stays constant equal to d, then the AR Sieve bootstrap may not work. Consider, for example, a situation where you look at the statistic using autocovariances. We know that the asymptotic distribution of the sample autocovariances in general depends on higher order moment structure of the underlying time series. So in this case, if you apply the AR Sieve, it is asymptotically not valid to do it. If you stay within the class of linear processes, and if you look at the statistic using autocorrelations, then it's clear that the AR Sieve also works for the case where the maximum lag dn is a constant. Finally, some finite sample results. We look at the following situations. So hypothesis testing, we use our max statistic to test if the autocorrelations are equal a specific value. And we consider linear as well as non-linear models. And basically, we see that in this situation, the ARC bootstrap works quite well. So we report here the empirical rejection rates for a certain number of observations, different nominal and nominal levels alpha, and different max levels for the max statistic. What can be said is that the results are, of course, not of course, but these results are better if you use the RSEEF bootstrap compared to doing a test using the Gumbel quantiles. So using asymptotic results in this hypothesis testing situation is not a good idea. So it's better to use the ARSEEF bootstrap. One final word about the final sample results is that the results for non-linear processes are not as good as for linear processes, which is kind of also related to this remark with fixed and growing dn. I'm looking forward to discussing our results further. This is the link to our paper. See you soon.